Hello everyone and welcome to the Robotics and Mechatronics tutorials in ROS. In this tutorial we will learn how to create a URDF file and a model of a four-wheeled mobile robot in Robot Operating System. This model is visualized over here by using RViz. It consists of a robot base represented by this red box and four wheels represented by these yellow cylinders. The base and wheels are called links in ROS terminology. Between the base and wheels we have four joints that enable wheel rotation. For example, over here I can rotate the first wheel. The robot is not moving simply because I didn't install the ROS controller that will enable movement. In this tutorial, for brevity and ease of understanding, we model a relatively simple geometry. However, everything explained in this video tutorial can be generalized and applied to more complex robotic geometries and CAD models. But before we start with explanations, we have to explain the main motivation for creating this video tutorial. Namely, online and on YouTube you can find a number of tutorials on how to model robots in ROS. However, to the best of my knowledge, these tutorials are either incomplete or obsolete. That is, they are not applicable to the current ROS Noetic distribution. Also, before I start with explanations, I would like to mention the following. It took me a significant amount of time, energy and planning to create this completely free video tutorial, as well as more than 400 free video tutorials that you can find on my YouTube channel. Consequently, I kindly ask you to press the like and subscribe buttons. Also, please feel free to leave any comment or a question you might have in the comment section below this video tutorial. Thank you. Okay, let's start. First, we need to install the necessary packages. Most likely you have these packages since they come with Noetic distribution. However, if you didn't install completely the Noetic distribution, it's always a good idea to try to install these packages. And who knows, maybe you don't have them. Click over here, then over here, search for terminal. Open a terminal window, and over here I will adjust the size of my terminal such that you can see in the background over here what I'm actually typing. First, I will try to install RViz. Let's do that. Okay, as you can see over here, I have RViz. Next, let's double check that RViz is actually working. Consequently, open a new terminal. You can do that by clicking over here and type ROS core. Then, in the original terminal, that is over here, try to run RViz by typing ROS run RViz, and let's see the output. Okay, so RViz is running. This is very important. Close this window, and next we need to install this package for URDF modeling. So let's do that. And obviously the package is already installed. Then we need to install this package. And this package is already installed. And then it's always a good idea to install this package. Okay, perfect. Now, let's close this terminal and let's open a new terminal such that we can start from scratch. Okay, here it is. I will adjust its size. The first step when you are creating a robot model or anything in ROS is to create a workspace folder. Over here, I will actually create the folder. The name of the folder is robot.dd. This will be the main folder of my ROS package, and inside of that folder I'm going to create a subfolder called SRC. You can change the name of this folder, that is robot.dd. However, it's very important that you have src or source subfolder within the main folder. Okay, next, let's change the current folder by typing this, and let's create an empty package. Then let's source this package by typing this, and let's verify that everything is properly sourced by typing this. Okay, we can see two things. We can see our new empty package and workspace, and this is the standard ROS Noetic source. Perfect. Next, let's go to the source folder by typing this. The next step is to create a ROS package, and to do that, I will type this command. To create the package, we're using catkin create package. Then we specify the name of the package, and you can change this name as you wish. In my case, it's robot.dd model package. And over here, I need to specify the dependencies. The first dependency is the package for C++ in ROS. The second dependency, tf2, lets the user keep track of multiple coordinate frames over time. The third package is this geometry messages, and this is a package for messages for common geometric primitives such as points, vectors, and poses. URDF dependency is actually a C++ parser for URDF package. RViz is actually a dependency for RViz, and the last dependency, joint state publisher GUI, contains a GUI tool for setting and publishing joint state values for a given URDF. Okay, so let's execute this command in Linux. Here it is, and voila. Let's see what's actually happening over here. Aha, we can see that this source subfolder contains a subfolder called robot.dd model package, and this is the main folder for our package. Let us create the necessary subfolders within this folder. To do that, we will type this to go to our folder package, and let's see what's happening over here. We see a few files and a few folders. Let's create a new folder. The name of this folder will be URDF, and this folder will actually store our geometrical description of robot, and another folder is launch folder. This folder called launch will be used to store files necessary to bring up the RViz. Okay, that's it. Let's see the outcome. Perfect. We have URDF and we have launch. The next step is to create a URDF file of robot geometry. URDF stands for Unified Robotics Description Format, and it's a very important file that completely describes the robot 3D geometry. So let's create such a file. First, I will go to my URDF folder, and over here I will create an empty URDF file. I will call it robot, and the extension should be URDF. Okay, here it is. Over here, I typed a simple URDF file defining the base link of my robot, and I will explain a line by line of this file. This part over here is always standard. That is, any URDF file will have this part over here. Over here, I wrote a comment. You start a comment with this set of symbols, and you end the comment like this. Over here, I start my robot description. I create a robot environment over here, and over here I close the robot environment. Here I specify the name. The name of the robot is 4-wheel robot. You can change this name as you wish. Then again, here is another comment. And over here, I start my first link. So what is a link? To illustrate the concept of links, over here you can see the top view of our robot. The robot consists of the body and it has 4 wheels. 1, 2, 3, 4. Any geometrical object, such as a link or a body or a wheel of a robot, is actually called a link in ROS terminology. Consequently, my body of the robot is actually called body link. And that's why over here I start the link environment and I close the link environment. When you define a link, you first need to define a visual representation of this link. Consequently, you start the environment visual and you close the environment visual. Within this visual environment, the first step is to define the position of the coordinate system that's located at the center of the mass of the link. And over here, I define that coordinate system. We have two sets of parameters. This set of parameters defines the rotation of that coordinate system with respect to some other fixed coordinate system, that is the coordinate system of the parent joint. And over here, I can see that the center of the mass of my body link coincides with the fixed coordinate system that's inertial in this particular configuration. Consequently, the center of the mass coordinate system of the body link does not have rotation or translation with respect to this fixed frame, and that's why over here I specify the rotation as 0, 0, and 0. R stands for roll, P stands for pitch, and Y stands for yaw. These are three Euler angles defining the rotations of two coordinate systems. And over 3 x, y, and z define the rotation. So it's 0, 0, and 0. Next, I need to define the geometry of my box. I start the geometry environment and the geometry environment, and over here I specify the box. The size is 1, 0.6, and 0.3. These are the dimensions in the x, y, and z axis directions. So let's see the figure again. 1 in the x direction, 0.6 in the y direction, and in the z direction I have 0.3. Perfect. And over here I define the material color. It's simply a red color. And visual, and link, and robot. And that's it. Next, let's save this file and let's visualize this box in RViz. Consequently, I will simply save this file, I will close the window, and you can see that the terminal is active. Next, let's create the launch file such that we can visualize the robot geometry in RViz. To create the launch file, we need to go to the launch folder by typing this. And over here, I will create an empty launch file. The name of the file is robot.launch. Over here, I type the launch file. Let's explain this file line by line. The first line should stay as it is. Every launch file should start with this code line. Over here, I create the launch environment and I close the launch environment. Over here, I specify the argument name, it's a model. Then, I specify this parameter name, it's called robot description. And over here, I need to specify the path to my geometric description of the robot. That is, I need to specify the path to my robot.urdf file. How do I do that? I use this command find robot DD model package, and this name should precisely correspond to the name of the package. That is, it should correspond to this folder name. And inside of this folder name, we obviously have another folder called URDF, and inside of that URDF, we have robot.urdf. So you need to type it like this. Next, I need to tell to my launch environment, that is, I need to tell to ROS the nodes that I want to launch. And I'm launching this node, joint state publisher. This node is used to publish states of different joints. Then I specify the package and I specify the type. Then I'm also starting with this node, robot state publisher. You don't need to know at this point more about this, you will learn it later on. And over here I need to specify to ROS that I'm actually starting the RViz, the package is RViz, and the type is RViz. And I'm starting with certain arguments. That is, I want to invoke this file inside of this folder. That is, at certain point there will be a file called robot.rviz inside of this folder. However, when you first start RViz, you will not be able to find this file. Never mind, that's completely perfect. We will create this file once we start RViz, and we close the environment with launch, and that's it. Let's save this file and let's close gedit. Next, let's create the complete package. First, go over here, and finally let's type catkin make to create everything. And let's hope that everything goes smoothly. You should always double check over here for errors. There are no errors in my case. And finally, let's run the environment. That is, let's run RViz. To do that, open a new terminal, and in that terminal start ROS core. Keep in mind that every time you want to run a ROS node or you want to launch something, in the background you need to run ROS core, and ROS core is a master ROS. Then, in the original terminal, we will type this. And let's see the output. Okay, here's RViz. However, we can see one problem over here. Where is our box? We don't see anything over here. To show the robot model, click over here on Add, and then over here you need to find robot model. So click over here. Aha, here it is. However, it's actually a white box. Over here, you need to adjust the fixed frame. Now, over here, the fixed frame should correspond to the frame that's defined in your URDF file. So let's bring up the URDF file, and the name should be body link. So let's do that. Let's type over here body link, and let's see what will happen. Here it is. Here's our box. Perfect. We can also visualize coordinate systems. We can do that by typing or by pressing here add, and over here you have several different options. You have this TF, which is also very important option to show. However, you can also explore and you can find other options. Axis is very important. So you can click over here, and under here axis you can see that it's a fixed frame, and that's it. So this is our fixed frame. This is the frame rigidly attached to our environment. That is, this is the inertial frame. Perfect. The next step is to save this configuration such that next time we open RViz, we start with these settings. To do that, click on File and click on Save Configuration As. And we need to find our workspace folder. I'll click on Home, and here it is. Then over here I click on Source, and I'll save the file over here. You need to specify the name of the file, and the name of the file is robot.rviz. Here, be very careful, since this name should completely match the name specified in the launch file. That is this name, and the path should be the same. That's why I'm actually saving the file called robot.rviz inside of this folder. And let's press enter, and that's it. Let's close rviz, and let's try to run rviz again by repeating this command, and let's see what will happen. Perfect. We are starting from the same configuration. Next, let's complete the robot model. To do that, close this window. Then, let's go to the corresponding folder. That is, let's go to the source. Then over here, we need to go to the robot.dd model package. Then we need to go to the URDF file. Here's our URDF file, and let's edit the URDF file. And over here, you need to specify the correct name. It's robot.urdf. Perfect. Here it is. We need to create this wheel. However, to create this wheel, we need to tell to ROS that this wheel can rotate around the body of our robot. That is, we need to create joint between the wheel link and the body link. Let's see how to do that. Here's our URDF file, and over here I will simply paste the piece of code. Over here I'm defining two things. First of all, I'm defining the joint, and I'm defining the link, that is the wheel link. Let's first explain the joint environment. The name of the joint is wheel1 joint, and you can change this name if you wish. Then, the type of the joint is continuous. This joint basically can rotate continuously around the body of the robot. That is, the rotation is not limited, and consequently the type is continuous. Next, I need to specify the parent and the child link. The parent link is the body link, and the child link is the link that I will create, and it's called wheel1 link. Consequently, I'm specifying the parent link is the body link, and that's precisely this link over here, and the child link is the wheel1 link. I will define the wheel1 link over here. Next, I need to specify the frame of this joint. Over here, I'm specifying the translation and rotation of the joint frame with respect to the fixed frame. That is the frame that's inertial and that's rigidly attached to my world. Note over here that this frame, that is this reference frame, is not necessarily the frame of the body link. In my particular case, the body link frame coincides with the first frame. However, in general, that might not be the case. I can see that my joint frame, that is the frame shown over here, is translated with respect to x, y, and z axis. The translation in the x direction is minus 0.3. The translation in the y direction is minus 0.35, and in the z direction you can see over here. Consequently, I'm specifying x, y, and z translations, and over here I'm specifying the rotations. The rotations will be 0, that is, the rotational angles are equal to 0 simply because the x, y, and z axis of my joint frame are parallel to x, y, and z axis of my first frame. Next, I need to specify the axis of rotation. Obviously, the axis of rotation is the y-axis, since this wheel rotates around the y-axis of the joint frame. And that's it. Now, I'm defining the wheel1 link. That is, I'm defining the wheel shown over here. First of all, I need to specify the center of the mass coordinate system. And the center of the mass coordinate system is defined now with respect to the wheel1 joint frame. That is, with respect to this frame. That is, everything is now defined with respect to this frame. Let's see the definition. Here's the origin, and I can see immediately here that I have a rotation around the x-axis, and this rotation is around this x-axis. Be careful. And I'm rotating with respect to, let's see the angle. The angle is 1.570795 radians. This corresponds to pi over 2 or 90 degrees. Why do I have this rotation? Well, if you would specify 0 over here, you are actually extruding this cylinder in the direction of the z-axis. However, once you extrude the cylinder in the z-axis, you need to rotate around the x-axis such that you actually obtain the wheel that's standing on the ground. And this is very important. And over here, I don't have any translation of the center of the mass of wheel with respect to wheel 1 joint coordinate system. That's why I have 0, 0, and 0. Over here, I define the geometry. The length of the cylinder is 0.1 and the radius is 0.15. And you can see over here the length and 2 times radius over here. Perfect. Let's continue. Then over here I define color. The color is yellow, and I close this environment visual, and finally I close link. Make sure that the file ends with this robot. Save this file, and let's try to visualize the result. To visualize the result, I will simply run once again from this window our RViz, and let's see the output. And here it is. Here's our wheel. Now let's try to rotate this wheel. To rotate this wheel, you can click over here to bring this window. You can expand this window to see what's happening over here. It's Joint State Publisher GUI. Now again, if you open the launch file, let's find the launch file. The launch file is located in my home folder. Here it is. It's under source over here, and I can simply click over here to open the launch file. You can clearly see the package GUI that you're bringing up. Here it is. And that's precisely this node over here that will enable you to actually rotate this wheel. So let's try to do that. Here you can see the angle of rotation in radians, and nothing happens. Well, nothing happens since you cannot see it, since this wheel is completely red and you cannot see the rotation. To see the actual rotation, click over here, and now you can see the wheel 1 link frame, and here it is. And now let's try to rotate, and we are rotating the joint and the complete wheel. Perfect. Now let's close this window, and let's go back to our robot.urdf file. In my case, the robot.urdf file is already open. However, you can open it by using gedit. The next step is to create this wheel. However, we learned that in order to create the wheel, we need to create the corresponding joint, and then we create the wheel. Let's do that. I will simply copy and paste over here the piece of code that I wrote. Here it is. The principle is the same. The name of the joint is wheel2, the type is continuous, the parent link is the body link, the child link is the wheel2 link. Over here, I specify the origin. You can see that everything is symmetric. It will be 0.35, 0.3, and in the z direction everything will stay the same. And the axis of rotation is the same. Then I specify the wheel2 link, that is, I specify my wheel. The rotations are the same, and the yellow color is the same. And that's it. Let's save this file, and let's bring up the RViz. To bring the RViz, simply type this part over here, and let's see the output. Aha, perfect. Now we have two wheels. Let's create the wheel 3 and the wheel 4. Over here is the joint tree and the wheel tree. Here it is. And I'm creating this wheel and this joint. First of all, I create a joint. I specify the coordinates. I specify the axis of rotation. And finally, I'm creating the wheel or the link. Here it is. Note over here that the child link and the body links are defined like this. This is very important. And finally, here's the fourth wheel. That is the wheel given over here. Again, first I define the joint, I specify the coordinates, I specify the axis of rotation, parent and child links, and over here I specify my wheel dimensions and rotation. And that's it. Save this file and let's open RViz once again. Consequently, go to the terminal and open RViz. And here it is. 1, 2, 3, 4. Let's try to move the wheels. Bring up this nice window that is our joint state publisher graphics user interface, and let's try, for example, to rotate this wheel. You can see the rotation by simply changing the reference frame, for example this one, then click over here and try to rotate. Perfect. Okay, that would be all for today. I hope that you liked this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.